Welcome to Summarize Science, where we break down complex research into simple terms. Imagine getting a medical scan from a high-tech, multi-million-dollar machine, but from a much smaller, cheaper, and more accessible device. That's the promise of a new AI framework designed to bridge the quality gap between low-field and high-field MRI scans. The problem is what researchers call a multi-aspect fidelity gap. Low-field MRIs are portable and affordable, but the images are blurry and lack detail, while high-field MRIs are precise, but incredibly expensive and immobile. Previous AI attempts to fix this often invented fake details or corrupted the underlying anatomy, making them unreliable for doctors. To solve this, researchers created the Cyclic Self-Supervised Diffusion Framework, or CSS-Diff. Think of it like an expert artist who doesn't just paint a pretty picture, but also checks their work constantly for accuracy. A key feature is cycle consistency. The AI learns to convert an image from low to high quality, but also from high to low. If the image it converts back doesn't match the original blurry scan, it knows it made a mistake and corrects its process, preventing it from hallucinating details. It also uses clever self-supervised techniques to understand the 3D context of the scan and to restore fine anatomical structures. And the results are pretty stunning. Here you can see a direct comparison between a real low-field MRI, images from various other AI models, and the image created by CSS-Diff. The CSS-Diff image is significantly sharper and more detailed, almost indistinguishable from a real high-field scan. Notice how fine structures, which are completely blurred out in the original, become clearly visible. But it's not just about looking good, the images have to be medically accurate. So, the researchers had expert MRI physicists rate the images across several criteria like image clarity, resolution, and artifacts. The AI-synthesized images were rated significantly higher than the original low-field scans and were found to be statistically comparable to the real high-field images in key areas. This improved quality has real-world diagnostic benefits. When they used the images to automatically measure the volume of different brain regions, the measurements from the AI-enhanced images were far more accurate. For example, volume measurement errors for structures like the hippocampus dropped from over 50% to below 15%. This shows the AI is preserving true anatomical detail, which is critical for clinical use. So, to recap, this new AI uses a powerful round-trip, self-checking method to reliably transform blurry, low-cost MRI scans into sharp, diagnostically useful images. It's more accurate and produces fewer artifacts than previous methods. The big-picture implication is a huge step towards democratizing medical imaging. This could bring advanced diagnostic capabilities to places that could never afford a high-end MRI machine, like smaller hospitals, rural clinics, or even mobile scanning units. It's a fantastic example of how AI can make advanced healthcare more accessible and affordable for everyone.